Okay, we start by constructing a graph of f of x equals x minus 1 times x plus 4 times x minus 3. In order to do the graph, the first thing we're going to do, because it's the first thing at this point that we know to do, is find the axis-intercepts. Okay, so the axis-intercepts, well, the y-intercept occurs, now this is written kind of small and not real clearly, but the y-intercept occurs where x equals 0. So the y-intercept is f of 0, because of course f of 0 is what you get when you let x equal 0. And the x-intercept is where y equals 0. So that means the x-intercept, or x-intercepts, is our solutions to the equation f of x equals 0. Why? Because y equals 0 and y equals f of x. Okay, so to say that y equals 0 is to say that f of x equals 0. Okay, well, the easier of the two tasks that we then have is to plug in 0 for x and see what we get. That's going to be our y-intercept. So f of 0, of course, is 0 minus 1 times 0 plus 4 times 0 minus 3, and that multiplies out to give us 12, so that the point 0, 12 is on the graph. So we, in the process of constructing the graph, and I'll put a small one in the margins here as soon as I find a reasonable piece of chalk. Okay, so at this point, that's going to be a small graph. Here's the bigger one, but that means we can put the point 0, 12 on our graph, and we know that the curve that we get for this function is going to pass through that point. Then, if f of x, if y is 0, f of x is 0, meaning that, well, this times this times this has to be 0. And that it follows by the 0 property in the fact that the only way you get 0 when you multiply three quantities is if at least one of them is 0. This says that either x minus 1 has to be 0, or x plus 4 has to be 0, or x minus 3 has to be 0 in order to solve this equation. So x minus 1 equals 0 is going to give you one solution, x plus 4 equals 0 is going to give you another, x minus 3 equals 0 is going to give you another, and thus, and ignore the purple stuff, that's stuff that I kind of add around the main thrust, which is in white, okay? So from these three equations, we easily solve each to get x. If x minus 1 is 0, then x is 1. If x plus 4 is 0, then x is negative 4. If x minus 3 is 0, x is 3. So that's three very, very simple equations. They aren't always that simple. You could have three different expressions of three different types, and each one might give you a fairly challenging equation to solve. Okay, but that would be all right. Right now, though, the equations that we get are very, very simple. Okay, well, now, I also comment that if x takes any other value, none of these are going to be 0. So when you multiply them, they aren't going to give you 0. This means the only place we can pass through the x-axis, the only place where y is 0, because that's what we immediately, I mean, that's why we're solving this equation. The only places where y can be 0 are at these points, which means that at x equals negative 4, x equals 1, and x equals 3, these are the only points the graph can go through the x-axis. Well, the next thing I asked people to do was sketch a smooth curve that goes through these points. Okay? And doesn't go through the x-axis anywhere else. So most people sketched a curve that looks like this. And people did this, and that made me fairly happy. Okay? And that's a perfectly good answer to the question. Okay? Now, there are other possible curves that could be drawn. So I drew this one, which was here in white. Okay? Then I drew a purple one and a green one that differed in some, each differing in some important way from the others. Now, when asked to do this, people will naturally, almost always, and that would include me the first time I did this, put the peak here, because there's a point there. Okay, well, you know, it'd actually be a little more natural. We're not turning in what I feel like is a real natural way. It'd be a little more natural to go up over this point a little higher and then down through and then back up. So that the peak doesn't occur here, it actually occurs here. Okay? So that's the purple graph that I drew. The peak is not going through this point. Okay? There is no reason to expect the peak to go through at the y-intercept. Matter of fact, I have a note here that says a peak at the y-intercept is rare. Whether you can read all those words or not, that's what it said. It'd be very rare that you would end up with a peak at your y-intercept. And then I've got the green graph where the peak is on the other side of the y-intercept. But of course, coming up through here, then to get through the y-intercept and to have a peak over here, I had to kind of curve this thing around here a little bit unnaturally. Okay? And then I had to come down very steep here and up. And the thing that's in this graph, and you wouldn't know it, and it's not even something we're going to talk a whole lot about, but this graph actually couldn't model your function here for reasons that really kind of go into the calculus and we're not going to talk about. And it's a little less natural. We kind of have to change our curvature kind of drastically to get through here and still come down through here. The purple graph is more natural and the white graph is natural enough. Okay? So I expect that the graph is going to look more like this. All right, so there is a set of three curves, any of which could model this function. Now, there's another way I could have drawn this curve. Okay, nobody did this, and it's a good thing because this isn't what happens for this function, but we can still go through all these points with a smooth curve by doing something like this. We come down here, up through this point, and then we level off and come down and level off asymptotic to our positive x-axis. Okay? This is still a perfectly good smooth curve, and there are some functions that might well behave like this, but a polynomial won't do this. Okay? In fact, the values of a polynomial, if you go far enough to the right, always end up being really big. Either positive big or negative big, but really big, one way or the other. And the same thing as you go to the left. It has to happen, and we'll see why. Okay. Now, we're going to go on and explore what happens, in fact, if we go further to the right or further to the left. So we'll do that next.